Hello, 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 ladies and gentlemen, and welcome back. We're looking in this video at question number 2 on the paper we just started last time, which was the Ontario Senior Math Problems Contest, or competition, I think, from 1968, ancestor to our Euclid paper. All right, so A part here, we got two parts here, but we'll start with A. Given that the equation x cubed plus ax squared plus bx plus c equals 0, so it's a monic cubic, I believe they call it, has roots r1, r2, and r3. Develop formulae for r1 plus r2 plus r3, r1 r2 plus r1 r3 plus r2 r3, and r1 r2 r3. All right, so this is something you probably have seen before if you're going to write the Euclid. So your roots are let's write out this polynomial. So it's xr1, xr2. Basically, we're just going to write it in factored form or root form or whatever the term is these days. And we're just going to compare coefficients, because the only way two polynomials are equal is if their coefficients are equal. Okay, if you look at all the ways to make x squared, you'll find that there's r1 minus r1 with these two x's, minus r2 with these two x's, and a minus r3 with these two x's. Minus r1 times r2 times an x. Same thing with an r1 and an r3, and an r2 and an r3x. And then your constant term is just going to be minus r1, r2, r3. And you could say something like comparing coefficients. We see that minus a is r1 plus r2 plus r3. B is r1, r2, r1, r3 plus r2, r3. And minus c is going to be r1, r2, r3. So that's what they asked for in part A. Just write it in factored form, expand, and equate the coefficients. C has to mean the same thing as minus r1, r2, r3. So minus c would just be r1, r2, r3. Okay, so nice little formulas there. Okay, now B here. For the equation, x cubed plus 2x squared plus 7x minus 19 equals 0, compute the values of r1 squared plus r2 squared plus r3 squared, and r1 cubed plus r2 cubed plus r3 cubed. Okay, so what can we do here? Well, I know r1 plus r2 plus r3 is negative a. If I look at negative a squared, that'll be r1 plus r2 plus r3 all squared. And that'll be r1 squared plus 2r1 r2 plus r2 squared plus 2r2 r3 plus r3 squared plus 2r3 r1. Now, if you want to write it out a bit more, that's fine, but I'm just going to square it normally there. Now, I've got what they want, but I've got some extra stuff here. So this is r1 squared plus r2 squared plus r3 squared. But it's also plus 2 copies of r1, r2, r2, r3, and r3, r1. Now I've seen this expression somewhere before. So we have some extra b's. So if I subtract off those two b's, I will be left with r1 squared plus r2 squared plus r3 squared. Okay, but they tell me in the question, I know that a is going to be 2 and b is going to be 7. Because they gave me a specific cubic. So I'll get minus 2 all squared minus 2 times 7. And that'll be 4 minus 14, and that'll be negative 10, which does not sit well with me. I would think a sum of squares would have to be positive. But no, the math is there. Everything's correct. So I guess what that would mean is that we've got to have some of these roots are complex. And you'll notice in part A there, they don't actually say the roots have to be real or anything like that. And they're not making that particular claim. Okay. So I guess we're fine. I'm a little uncomfortable about it. That's all. But okay, so now we can move on to R1, or R1 cubed plus R2 cubed plus R3 cubed. I think we can probably handle it in basically the same way. Right? And we should be able to do that. So now we could start with minus a cubed. Another thought occurs to me, we could take the expression we already know from not the sort of the first part of this question, and we could then multiply that by R1 plus R2 plus R3, right? So that certainly seems, and so we'd just be multiplying by an extra minus a. I don't know which one's better. I think I'm probably tempted just to go with the one that I've got here. I think that's easier. So expanding that out, you'll get R1 cubed plus 3R1 squared R2 plus 3R1 R2 squared plus R2 cubed plus 3 R2 squared R3 plus 3R2 R3 squared plus R3 cubed plus 3 R3 squared R1 plus 3 R3 R1 squared. And then there's going to be... So I'm just sort of foiling this out in my head, by the way. Or foiling it, or George. I'm just expanding it out term by term in my head. Okay. Now in total we should have 27 expressions, because I got 3, 3, and 3. So 3 times 3 times 3, 27. 3 and 3, 6. 3 and 3, 6. 3 and 3, 6. So that's 18 so far. And then 1, 2, 3 is 21. So we should get 6 copies of R1, R2, R3. 3 choices for which single one to pick here. Only 2 choices, because, if I pick R2 here, I can't pick R2 here. And yeah, okay, 6 makes sense. Okay, so we get 6 extra copies there. Okay. So we've got the thing we want. R1, R2, or R1 cubed plus R2 cubed plus R3 cubed. And then I've got 6 copies of R1, R2, R3. Well, that's 6 copies of C right there. Sorry, 6 copies of negative C. Okay. And then we've also got these expressions in here. And how can you make those? Well, you can definitely take out a factor of 3. And for some of them, you get an extra R1, R2, and R3. I think if we do something like this, I'll get 3. R1 with these will be R1 squared R2. You will get 3 R1, R2, R3s in the middle here, but then you'll get 3 R3, R1 squareds. And you'll basically get the same thing over again it should be plus signs. R1, R2, R3. So we get some extra copies of negative C, but we also have the thing that we want. Okay, so R2 and 2 copies of R3, and then 2 copies of R3 and R1. Alrighty. So that is 3 negative A times B. That gets the things I want, but also 9 copies of negative C. So if I want to get rid of those, I need to subtract 9 copies of negative C. So I basically need to add 9 copies of C. So these blue bits here are negative 3AB plus 9Cs. And this bit here is minus 6Cs. So we're going to add those together and say 1, 2, 3, 4, 5, 6, 7 should all turn into negative 3AB, minus 6Cs and 9Cs will cancel out to be plus 3Cs. Okay, so to summarize, minus A cubed is the thing we want. Plus 3C minus 3AB. Let's go back and double check. Yes. So I'll bring it over to the other side. So this will be minus A cubed plus 3AB minus 3C. That should give me what I want. A was 2, B is 7, and C is negative 19. Minus 2 cubed, so that'll be minus 8, plus 3 times 2 times 7, minus 3 times negative 19. That'll be negative 8 plus 42 plus 57. So that'll be 99 minus 8. We should get 91. Okay. So to summarize for them, for whoever would be marking this, we got this is minus 10. So I'm accepting that some of these roots are complex, because the math isn't going to lie. And they didn't say the roots had to be real. And to be honest, they might have been more comfortable with complex numbers. We don't see it as much these days in high school. I remember when I was going through high school, we only did it for maybe a week of class in grade 10. Never talked about them ever again. But there we go, there's our answer. Now, one other thing we could do, just while I'm thinking about it, we didn't have to necessarily do it the way we did it a moment ago. We are given, for the R1 cubed, R2 cubed, and things like that. So here's another way to do it. We know that R1, R2, and R3 are roots of this particular polynomial. So if I plug them in, I'll make the whole thing equal to 0. Okay, these are the only numbers I get to do this with. So I know these equations are all true. Now if I add them all up, over here I get the R1 cubed plus R2 cubed plus R3 cubed. Here I'll get 2 copies of R1 squared, R2 squared, and R3. Well, we just said that was negative 10. We actually had to work that one out, but now we've got this. 7 copies of R1 plus R2 plus R3, but isn't that negative A? So isn't that negative 2? And then minus 57 here. So that should equal 0. So bring all this over to the other side. R1 cubed plus R2 cubed plus R3 cubed should be 20 plus 14 plus 57, and we can see once again we get 91. Yeah, 4 here makes that 61, plus 10 is 71, plus 20 is 91. So that's another way to get that. And actually, if you're even more curious about this stuff, they're not asking about the question, but I do like this sort of symmetric polynomial work. If you were curious about, say, r1 to the 4 plus r2 to the 4 plus r3 to the 4, they're not asking about that one. But all you would do is take these equations that we just did here and multiply them by r1, because that's not going to change anything, because you just multiply over the 0 over here by r1. And so you can get this same sort of work. And so earlier calculations inform the later calculations. So that's really nice. Okay? And the same sort of thing also, I'm going on about this. The same sort of work can also help you find roots and expressions involving larger polynomials. There was nothing special about cubics here. Okay? So there's a whole wide world of these things to explore, and each of the A's, B's, all the coefficients here can be expressed in terms of what are called symmetric polynomials. In fact, I think they're called the elementary symmetric polynomials in however many roots you've got. And really nifty stuff, but I'm going to leave it there because I don't want this video to be really long and me talking about a whole bunch of symmetric function theory that we don't need. We've got more of this Ontario Senior paper to look at. And up next is going to be question number 3, so we'll take a look at that in the following video.